Now we're looking at the fundamental theorem of algebra. If the function f(x) is a polynomial function of degree n greater than or equal to 1, then f has at least one complex zero. One thing I want us to recall is that all real numbers are complex, as well as the imaginary numbers. So one concept that comes out of the fundamental theorem of algebra is about complex zeros. Note, every polynomial function f of x of degree n has to be greater than or equal to 1, it has exactly n complex zeros. Some of these zeros may be imaginary and some may be repeated. Non-real zeros occur in conjugate pairs. In other words, if you have an imaginary zero of a plus bi, then there also exists an imaginary zero of a minus bi. Now remember, only the real zeros are going to show up as x-intercepts. So if there's no x-intercept, that means that they have complex or imaginary zeros. So let's look at the first example. We want to find all of the zeros of the function f of x equals x cubed minus 2x squared plus 3x and write it in factored form. We first want to try to factor the function if possible. Notice there's a GCF of x, leaving us with an x squared minus 2x plus 3. Unfortunately, the x squared minus 2x plus 3 is not factorable. It looks like it might be, but it's not. So we would use the quadratic function. So we would take the opposite of the b plus or minus the square root of the b squared minus 4 times a times c, all divided by 2 times the a. And when we simplify, notice we get a negative underneath the radical. We would simplify that 8 like we normally would, the square root of 8. We would get 2 rad 2 over 2, but we would also have an I value. And for those of you that may have forgotten how to simplify that square root of 8, a couple of ways. We can write it as the square root of 4 times the square root of 2. But we can also continue with that 4, get 2 and 2. Remember, we're looking for pairs. So the pair comes out. The one that does not have a pair, he stays in. We can also divide everybody by this common factor of 2. And notice everybody has to be divided by the same number. And that leaves us with 1 plus or minus the square root of 2i. Also notice that the I is not underneath the radical. So all of our zeros come from this factor of x. We can't forget that guy. And these two that we found using the quadratic formula. So we have an x of 0, 1 minus the square root of 2i, and 1 plus the square root of 2i. Notice they wanted us to write the equation in factored form. Well, we already have x as a factor because we factored it out. The complex numbers sometimes look a little strange. It's always x minus that 0, so it would be minus parentheses 1 minus the square root of 2i, and x minus parentheses 1 plus the square root of 2i. If we were to distribute that, we would get x minus 1 plus the square root of 2i, and x minus 1 minus the square root of 2i, as well as the single x factor in the front. In this example, we are asked to find the equation of a degree 3 polynomial with zeros of 2/5 and 3 minus I. Assume the leading coefficient is 1. Well, remember, if we're given the zeros, we can go backwards and find the factors. So the function f of x would have the factor x minus 2/5 times x minus the binomial, notice I put a parentheses, the binomial 3 minus I, but 3 minus I is imaginary. So remember, if it has a zero of 3 minus I, it must also have a zero of 3 plus I. And that satisfies our theorem that says if it's a degree 3, then it has exactly 3 zeros, complex zeros. So we can clean this up. Notice in that first factor where we have x minus 2/5. If 2/5 is the zero, that means that we can also write this as 5x minus 2. We bring that bottom up to that x. If we were to solve either of those factors, we would still get a zero of 2/5. Our second is x minus 3 plus I. And our third, distributing that negative again, is a negative 3 minus I. But they're wanting us to find the equation. Sometimes they will say, find the equation, and they want it expanded. Sometimes they say you can leave it in factored form. The general rule, if you're dealing with imaginary numbers, such as the 3 minus I or the 3 plus I, they want you to at least multiply out those two binomials so you no longer have imaginary numbers in your answer. So let's do that. Let's go ahead and expand these two first. We're going to need a little room, so I'm going to write a little bit smaller. We have the 5x minus 2, and now we're going to distribute. X squared, x times negative 3, negative 3x, negative xi. Now let's distribute the negative 3 here. This guy. We'll get a negative 3x plus 9 plus 3i. Now let's distribute the I, and we get plus xi minus 3i minus I squared. And remember that I squared is actually a negative 1 by definition. So we continue with that first binomial, 5x minus 2. And if we've done it correctly, anything with an I, with that imaginary number, it should add up to 0 or reduce. So let's see, we have an x squared. We have a negative 3x, a negative 3x to give us a minus 6x. This negative xi and this positive xi reduce. We have one constant of plus 9. And then we have positive 3i and a negative 3i that reduce. And we also have minus the negative 1 at the end, which would become plus a positive 1. So we have 5x minus 2 times x squared minus 6x plus 10. And if they don't ask you to expand it, I would leave it right here.